Okay, welcome to your second video lecture in section 10.5 on separation of variables, heat conduction, and a rod. In the last lecture we derived this initial boundary value problem for the heat inside of a rod of length L. To solve this heat equation, what we're going to do is go through the method of what's called separation of variables. Okay. In some sense, what we do is assume that the solution u can be written as the product of a function purely of x and a function purely of t. If we do that, as with all of our guesses in this course, what we have to do is plug that back into the differential equation. The first partial of this guy with respect to t will only alter t and make it t prime. The second partial with respect to x will only alter this guy and make two derivatives with respect to x. We go ahead and solve this equation by rearranging to obtain this equation here. And this equation can only be true. A function of x, that's only a function of x, and a function of t can only be equal to each other for all values of x and t if it's constant. Okay? And so what we'll do is we'll call this constant negative lambda. We've been used to lambdas here. And so if both of these equations are equal to negative lambda, then x double prime divided by x is equal to negative lambda, which gives us this second order problem in x. And t prime over alpha squared t is equal to negative lambda, giving us this first order problem for t. Okay, what we'll do is we'll first focus on this second order problem in x. This looks very much like a boundary value eigenvalue problem. So to complete this problem, we need boundary conditions. Since at 0, the solution is 0, and we don't want our actual solution to be the trivial solution, right? If our solution is x and t of t, if t of t is 0 for all t, then our solution is 0, and we don't want that. And thus, x of 0 must be the thing making this guy 0. Similarly, at L will also be 0 for the very same reasons. What we have is a boundary value eigenvalue problem for x. We know how to solve that boundary value eigenvalue problem. We've done it before. The eigenvalues here are n squared pi squared over L squared, and the eigenfunctions are sine of n pi x over L. Okay? So now that we have the lambda n's, we can plug that into the first order equation for t. And this is just a first order linear equations for each n, which we know we can solve to make t equaling negative exponential functions. Okay, we still haven't resolved the initial condition, so each one of those tn's has an arbitrary constant with it. Because our partial differential equation is both linear and homogeneous, we can superimpose all the solutions together. So we can add all these un's, which is the product of xn and tn, which is the product of these exponential and sine functions, to obtain this infinite series of exponentials times sines as our solution. We still haven't resolved the arbitrary constants, and so to do so, what we're going to do is use the initial condition. Okay? When t is 0, the exponential functions go away, and what we have is that f is equal to this Fourier sine series. And so the CNs are just the Fourier sine coefficients of f. Okay, in the next lecture what we're going to do is apply this to an example.